Hi, Miss Juliana, good evening. Please confirm you can hear me.
Yes, I can hear you. Can you hear me?
Yes, I can hear you. All right.
No, I can't see anyone joining the call.
Give me a minute. Let me call again. Good evening, Daniel. Thank you for joining in. So I'm still expecting your students to join in the call. I've not seen a couple of them, so I for what's happening. Confirm you can hear me.
Yes, I can hear you. Good evening. They'll join in shortly.
Good
They'll
evening.
join in
Tayo.
shortly.
All right.
Hello, good evening, everyone. Please confirm you can hear me.
Yes, we can hear you.
All right. We'll be starting shortly. First, and before we just begin, I would like to welcome you all to this ALP, Juliana Uche. I'm the ALP lead for SC1 reception. And in a few seconds, I'll be handing over to the moderator, the president of K Goodness of 4. She's the program's chair for SC Unical. She would be the one to lead us and steer us throughout the course of this ALP program. Heather Goodness, if you're on the call, please kindly unmute and go ahead.
Okay, thank you very much, Miss Juliana. Good evening, everybody. Welcome to today's session. Please confirm that you can hear me before I continue.
Yes, we can hear you.
Okay, thank you. So, good evening, everybody. Welcome. My name is Kede Goodness of 4, just as was earlier introduced, and I'll be your moderator for today's session. So, sit back, relax, and I encourage you to actively participate. Our theme today is the fundamentals of cementing. If you have any questions, there'll be a time for you to ask that. Just, enjoy yourself and prepare to learn. So very quickly, we'll be moving on to the next item on our list, and that is the safety moment from Ms. Bethel Itohan, the Vice President, SPPTI. Ms. Bethel, you can take the floor.
Okay, good evening, everyone. My name is Oliabele Beto Etohan. I'm the Vice President of SPPTI chapter. So I'll be taking the safety brief. This is to encourage safety during this call. Mute your mic when not speaking. So whenever you're not speaking, just mute your mic. Raise up your hands to speak. You see it on the chat box. Just click on the icon, raise up your hands. Then ensure you can still hear the fire alarm with your headsets. These are for those of us using headsets or AirPods. Then use the chat buttons, C for comments and Q for questions. Maintain a good sitting posture. These are for those sitting down to avoid back pains. And be at alert and aware of your environments. Thank you. I want to make sure that all of us will all ensure these safety briefs. So over to the moderator. Thank you.
Okay, thank you so much, Ms. Bethel. Just as she said, mute your mic when you're not speaking so that the call will not be rowdy. If 3 mics are on, it's going to create a very uncomfortable environment. If you need to say anything, raise your hand, especially during the question and answer session. Do not speak out of turn. Wait until you're called for. Raise your hand and speak. Use the chat box button if you need anything, so that we could all enjoy this session and everything would go very smoothly. Now, the very next item on our list is the opening remarks, and this will be handled by the membership co-lead, Mr. Matthew Godwill Bright. Mr. Matthew, please go ahead, sir.
Okay, can everyone hear me?
Yes, we can hear you.
Okay, all right. Thank you very much. Just for the sake of time and network issues, Mr. Matthew is having some network glitches. I'd like to call on one of our very senior YPs, senior young professionals from the section. We're privileged to have all on the call, the president of Galaga Organization. Ma, please, if you can hear me, I would love for you to help us with the opening remark.
Sorry, good evening, everyone. Are you calling me to take the opening remark or
Yes, yes, please. Thank you very much.
Okay. Good evening, everyone. And thank you very much, Juliana. And for today's session, I just want to encourage us to pay attention to what the speaker will be saying, especially in cementing, because to produce from a good well, you have to ensure that there is proper cement job. I don't know if most of us are familiar with the Deepwater Horizon and what happened. So if you are familiar with that, you understand that a cement job is very critical in the oil and gas industry. So today's topic that emphasizing on how to design, the basic knowledge of cementing in the industry, information you need to know, then the things that you need to also avoid as petroleum engineers or as other related fields that you may be in. So do well to your journal, your notebook, write things down, and also encourage people to use the LinkedIn for their own benefit. So at the end of today's session, you may want to go on LinkedIn and you post, okay, this was what I was able to understand from today's session, how it applies to what I'm currently studying in school or what I'm currently practicing in the field. It's not only about cementing, it's also involves safety, because there's really no job in the industry that you can do without safety being implemented properly. So thank you very much and welcome to the ALP for this day. I think this is the last day of April, so do well to have a very beautiful session. Thank you. Over to you.
Oh, thank you so much, Ma. Thank you. I'm sure you've heard what she said. Be prepared to learn, get your notepads and your pens ready. If you have questions, do not be shy. Ask them when the time for questions would reach. So moving on, we'll be going to our icebreaker session, and this will be taken by Miss Ebby, an ALP co-lead from the Worry section. Miss Ebby, the floor is yours.
All right, yeah, thank you, Kedo. I can hear you. Good evening, everybody. All right, so we'll be taking the icebreaker session right about now. So the icebreaker session is more like to prepare us for what is to come. It's more like a seed. We are sowing a seed for what's to come, right? So the speaker is going to be watching this later. So we just want to give an insight of what you're going to experience during the session, right? So we have about 6 questions, and I would like to encourage each and every one of you to make use of the chat box to give your responses so that I can read as well. So we're just going now. Thank you very much. Next slide. So the first question we have, cementing is one of the most important operations in drilling. Yes or no? Do you agree or disagree that cementing is one of the most important operations in drilling? Okay, so we have Kene Shuku from UI said, I agree. Daniel says he agrees as well. All right, everybody, almost everybody. So yeah, we have a large audience with the agreeing button. So let's move on to the next question. So the next question says, how long do you think a cement job takes in real life? This is something I've not really thought about, Sha, probably because I've not been there. So how long do you think it takes? Do you think 30 minutes, 2 days, 3 days, 1 week, a month? Let me get your options, your opinions rather. So let's see. How long do you think a cement job takes in real life? Nobody's responding. You're quite slow. All right. Somebody said 2 days max. All right. Daniel says less than a week, depending on the whole session. All right. Let me see if I would see any other. Okay. Similane said 1 and more. Better said 2 to 3 days. All right. It's like people have been on the field before, but that's fine. Let's move over to the next question. All right. So our third question, we have we have 2 options here, and you have to pick which one scares you more. So we have one which says the cement job failure or a blowout. initially, Miss FJ was talking about the Deepwater Horizon incident. It was caused by a blowout. So yeah, somebody said blowout. All right. Callisto said A. How is cement job failure the one that scares you more? All right, no problem. Maybe there's something to it. I don't know. We'll find out in this session. Let's move over to the next question. Okay, question 4 says, you are on a rig and a cementing operation goes wrong. What's your move? A, act confident but you are lost. B, call senior immediately. Or C, try to fix it first. Okay, Similarly said, try to fix it first. And Keneshiku is saying you can't do anything about a blowout. You can remediate during field smelting. Okay. Kalisa says you'll find Kalisa says you'll find the nearest ocean. That's really crazy. I don't know how to swim. Maybe you know how to swim. That's fine. So let's move over to the next question. All right. Michael rather says is going to call his senior. So question 5, cementing is just pumping cement into a hole. Is that a myth or a fact? Let me hear your thoughts. Okay, Timilei says it's a myth. All right. Cementing is just pumping cement into a hole, like Dangote cement, Abibwa cement. I really do not know. We're going to find out today. Keneshiku is also saying it's a myth. So we have more responses with the myth thing. So moving on to the last question, last but not the least. Let's see what we have. Okay, I'm going to answer this. What's one word that comes to your mind when you hear the word cementing? What's one word that comes to your mind when you hear the word cementing? I think for me, it's well completion. I think, yeah, that was what I thought first. Well completion. So confidence says casing. Similarly said controlling. Callisto said Dangote. Callisto, is this your responses? Bright says pressure. Keneshiku said drilling. All right, thank you very, very much. So during the course of this lecture, we are going to see all of these things, how they relate, all these questions, how they relate to it. So thank you everyone for the responses. Over to you, Kede. Thank you so much.
Thank you so much, Ms. Bethel, for that. So it is at this point that we'll be moving to introduce our guest speaker. I mean, this is what we are all here for, right? We are here to know the fundamentals of cementing, and I'm sure he has much more than that for us. So join me to welcome Mr. Clement Moses Ola to come and do the introduction of our guest speaker. Mr. Clement.
Okay, Kede, I don't think Clement is on the call because he complained earlier that he has some network challenges due to the rain that's falling in Calabar right now. So I think someone else would have to take the introduction.
All right. Good evening, everyone. Can you hear me?
Yes, we can hear you.
All right, just in a step, I would love to introduce our guest speaker for today. It's a pleasure to introduce him. But just before I go on, I would like to recognize some very important dignitaries that have joined us here on the call today. We have some very senior YPs on the call, the president of Callistus Oshule, our graphics team lead. Thank you very much for joining us. I would also like to recognize Balaga Ogenefejiro. Thank you very much for joining us. And it is my distinct honor to read the bio of our speaker today, the person of Amos Akpoduma. Our speaker today is a petroleum engineering professional with strong field experience in drilling operations, well-site supervision, and rig auditing within the oil and gas industry. He currently works as a well engineer where he's responsible for designing and planning well construction activities to ensure safe and cost-effective delivery. In his role, Amos combines engineering design with real-time operational support, working closely with drilling teams and service companies to execute well programs, manage risks, and optimize drilling performance. His background also includes hands-on experience as a well-site drilling engineer, giving him practical insights into field execution and decision-making under operational conditions. With a solid blend of engineering knowledge and field experience, he continues to contribute to efficient and safe well delivery in the energy industry. It is my pleasure to welcome our ambassador for today, person of Mr. Amos Akwaduma. He is an add-ons volunteer, also in SP and the ALP as well. He's a content development lead. So please, if you're on the call, please kindly unmute and bless us with this amazing lecture for today. Thank you.
Thank you very much, Juliana. Good evening, everyone. Please, you guys should confirm that you can hear me.
Yes,
Hello,
we
please.
can hear you. Yes, we can hear you.
Yeah, if you can hear me, please make me a co-host so I can share my screen. AB, please make me a co-host so I can share my screen, my slide rather. Please confirm you can see my slide. Hello, guys. Please confirm you can see my slide.
Yes, we can. Yes, we can.
All right. Good evening, everyone. I'm really excited to be here with you guys. So basically, I will just run through fundamentals of cementing from theory to field application. So my learning objective for this presentation is just very, very simple. Since we are talking about fundamentals of cement, so everything I'm going to be saying will be limited to primary cementing operation. So from pilot test in the lab straight to operations, cementing operations on the rig site. So I believe you guys will gain value from this presentation. And again, before I continue, during the icebreaker section, there were some questions that were asked. I think I jotted some down. I saw some answers also, some funny answers and all of that. Please, you guys should confirm you can still hear me. Hello, guys. Confirm you can still hear me, that I'm not talking to myself.
Yes, we can hear you loud and clear. Yeah.
Okay, please. For the purpose of this presentation, I want it to be as interactive as possible. If I ask a question, please, somebody should unmute and respond. I don't want it to be rowdy, but please let it just be as interactive as much as possible. So for the icebreaker section, I think some questions were asked, like, I think one of them was, what do people fear most? Paraphrasing right now, what do people fear most? Cement failure, which is post cement job, or a blowout. I think some people were saying a blowout and all of that. It was A and B. Actually, in reality, A can actually lead to B. So post cement job can actually lead to a blowout. I just want us to know that. And then again, the other one was how many days does cementing operation takes in the rig site or in the well site? Actually, there how many days? In my own experience, I even spent more than 10 hours in cementing operations. I think it's usually between 6 to 8 hours in my own experience. So, and also it depends on the depth and all some other factors. So it doesn't take this unless probably you're having issues. It's not a primary cementing job and all of that. So my outline for this presentation. I'll be taking you guys on introduction, function of a cement, classes of cement, and then we will wrap it up with a little cementing calculations. So I believe most people on this call, they are students. So I would like you guys to just get your calculator in handy. So when we get to the calculation, we can easily do a little thing, because we are going to be practically what this presentation is going to be like is more like we're engineers designing slurry for cementing operation. So what is a cement? I can't really see chat box. Can someone just unmute themselves and tell me what a cement is, please? Hello, guys. Hello,
We
guys.
can hear you, sir. We can hear you, sir.
You guys can still see my screen, right? I'm not getting any feedback from you guys.
We can see your screen. We can see your screen.
Okay, I was asking a question. Somebody just unmute themselves and just tell me what a cement is. What is cement?
Okay, let me attempt to answer the question. Good evening.
Alright.
Please confirm if you can hear me.
Yeah, loud and clear.
Okay, this is Daniel from University of Calabar. So in my attempt to define a cement, I'd say a cement is a fine mixture of which its main component is calcium trisulcarbonate or limestone, which is primarily used for binding materials together when mixed with water and other additives. I don't know, that's the best I can do for now.
All right, thank you very much, Daniel. So in reality, that's just cement. Cement is just very, very simple. That's just all. Give me a second, okay? All right, so that's just actually cement. If you can see my screen, this is a cement. There's no other definition than what Daniel has already said. This is your cement. You can attribute cement as what everybody has always been saying, which is, I think most of us, we are familiar with Dangote cement, right? Can you guys hear me? Okay, I can see a response now. So most of us are familiar with Dangote cement. So Dangote
Yes, we
cement
can hear you loud and clear.
yeah, so Dangote cement is just like the definition of what a cement actually looks like, what an oil and gas cement actually look like. But though different properties, different mixture and all of that, different additive, but that is what cement, that's what cement is. So give me a second. Sorry about that, guys. All right. So before we talk about cementing, we assume that some of us here have not actually gone to the field. So if you go to the field, cementing operation is one simple operation. In fact, drilling operation at large, in my own experience, it's one of the simplest operation in petroleum engineering. That is what I believe. It's that simple. So I'm just going to be giving you guys a little representation of everything we do in the well site on the rig. When you get to the rig, you already have a cellar. A cellar is just a hole that's already been dug. You already have a cellar. So what do? You make a hole, which you drill. The hole you drill becomes your open hole. After drilling, I think petroleum engineering guys on the call, we know these things very well. You case. So after running your casing, what's next? You cement. So these three things that I just showed you guys now, the drilling for the open hole, then the casing and cementing, is practically the description of everything we do on the well site. The other things that come in is probably formation evaluation. You want to evaluate the hole you've drilled, etc. You want to complete them and all of that. But basically what you do in drilling is you drill, you case, and you cement, and that is all in drilling. So I think this falls back to our question on the icebreaker. Once the question was asked that what do you fear the most, a poor cement job or a blowout? For petroleum engineers, how many of you are familiar with this on my screen here? If you are familiar with it, just unmute yourself and say, yes, I know about the Deepwater Horizon. I can't see the chat box. I would have actually, okay, I can. All right, I can. Let me check it. Okay, so I can see yes on the chat box. Okay, this is Deepwater Horizon. And what happened in Deepwater Horizon is just simple. It's just a poor cement job that wasn't resolved and led to a blowout. I think that's one of the biggest disasters in the oil and gas industry. So as simple as cementing operation is, it's very, very, very essential and very, very important in the life cycle of drilling operation. Are you guys still with me?
Yes, sir, we
Yes,
can hear you.
sir, we can hear you.
All right, okay. So basically, this is what a cement is. A cement is used primarily as an impermeable sealed material in the oil and gas well drilling. So basically, like the schematic I showed earlier, one of the most widely used of cement is actually to bond the casing to the formation. It's that simple. I'm trying to be as simple as possible in my explanation. So, and in case, as I'm going, please, if you don't understand anything or you are kind of lost, you can draw my attention to it immediately, please. So this is what cementing is. Basically, this is what is most widely used for. But you should know that that is not the only thing cementing is used for. Cementing operations can be done for other stuff. You can have, if you want to probably, for remedial operations, you will need a cementing job. If you want to abandon a well, you will need a cementing job. If you want to sidetrack, you still do a cementing job. So cementing job in the industry is quite large, but then again, like I said earlier, my learning objective for this is to streamline everything I'm going to say to primary cementing operation. If you guys can see my screen, these are some of the functions of cementing. This one here, the very first one here, restriction of fluid movement from between permeable zones. That is the most important. You should know this, like a rule of thumb. That is the most important use of cement. The most important function of a cement is not actually to prevent caving in, like we all know in school. Caving in, isolate, caving in, hold the casing and all of that. That's not the, should I use the word primary function of a cement? We should know this as a rule of thumb. The primary function of a cement is to actually restrict fluid movement between formation. You don't want a cross flow of fluid in your formation. This can lead to channeling, blowout, etc. So that's just the major, like the primary function of a cementing. Other functions include provision of mechanical support to casing string, protection of casing from corrosion. Cements usually are additives like corrosion resistance are added to it so that your casing does not rust or does not corrode over time. I use rust because I think most of us will be familiar with that language. It's also support of the well-bore walls to prevent collapse, etc. This other part of my slide, the right-hand side, you guys can see a schematic diagram here. Who can tell me you can use the chart box for this schematic diagram. Who can tell me the major difference between this schematic diagram? We can use this chart box, please. I'm still waiting on you guys. You guys just look. What's the major difference between these two diagrams here? Okay, I can see liner. All right, go ahead. Okay, I can see there's no intermediate casing in the second diagram. That's a confidence. Okay, liner wasn't used in the first one. All right, guys. Thank you very much for that. Okay, the major difference, you guys are not wrong. Everybody that gave their response, there's no liner in the normally pressured zone. The abnormally pressured zone, there's a liner, etc. But what I want you guys to actually take cognizance of is actually the intermediate casing. On the rig site, most operations don't use the intermediate casing. We only use intermediate casing probably when there is an overly pressured zone. That's why if you see in the first diagram, the first schematic, you see a normally pressured, and the second schematic is abnormally pressured. So if we're having a very high pressured formation, high pressured zone, we want to use an intermediate casing. We don't want an issue as we are drilling further. So that's what I want you guys to actually pick from this. Thank you very much for the guys that interacted. All right, so right now, I'm going to be talking about the classification of cement. So all the cements we use in the oil and gas industry, this is the classification. We have API classification and other classification. But basically, like we all, I don't use what like we all know because I know there are some students on this call. But like we should know, API is more like the policeman of the oil and gas. They are in charge of standards and all of that. So for API classify cement into A to H. So there's a class A cement, there's a class B cement, there's a class C cement, there's a class D, E, F, G, and H cement. So these are the classes of cement according to API standard. Also, there are other classification of cement like the POX mix, the gypsum cement, and all of that. But for the purpose of this presentation and for future, for the students that are going to be into drilling operations, or for, as a rule of thumb, let me use it that way, as a rule of thumb, you should know that the most common and the most used classification of cement or type of cement in the industry is a class G cement. So if you don't get anything out of this presentation today, I want you to just know this, that the most common, the most used cement in the oil and gas industry is the class G cement. The other cement, we can use class A and B for shallow wells, class A, B, C for shallow wells, and D, E, F for deeper wells, but the most commonly used is the class G cement. For the Portsmouth cement, it's just Portland cement plus additives like bentonite, volcanic ash. Gypsum is similar thing. All right, so we'll be moving to the cement slurry, how cement slurry are actually designed. First off, we already know what a cement is already. Like Daniel helped us to define. We already know a cement is just a fine particle made from limestone, shale, whatnot. So how do we design a cement slurry? First off, I said we already picked the type of cement we are going to use, which is a class G. That's the most common cement. So if we are designing a cement slurry, we already know, oh, we're picking a class G API standard cement. So first off, we'll be talking about the mixed waters, the cement mixed water. So what is cement mixed water? Is already here. So mixed water is the water that is used to make up the cement. It's more like, I think it's self-explanatory. If you want to mold a block, the water you use to prepare your cement, make your cement, mix your cement, that is the mixed water. There's no big English to it. That's why I said drilling engineering is one of the simplest form of petroleum. It's one of the simplest discipline in petroleum engineering. So the amount of mixed water we use is based on the need to have a slurry that is pumpable. We want to make sure that our slurry that we're going to design is easily pumpable. We can mix it on the surface and pump it into the wellbore. We don't want a cement that we are mixing and is flash setting. When I mean flash set, like it's already getting hard, it's already setting, it's already getting hardened. We don't want that situation. So our mixed water is very, very, very important while mixing our cement. So I will need to make sure that all our cement, all the fine powders are well hydrated. If you guys can see me, just drop an emoji on the chat box. If you're understanding what I'm saying, if I'm rushing, please, I need feedback. All right. Okay, so on the right side, there's a table here. This table, like I said, these are standard by API. These standards they are. All right, thank you very much. I can see everybody on the chat box. Thank you. Okay, let's move ahead. So like I was saying, for this table here, these are standards by API. So for API standard for a class G cement, our mixed water gallon per sack, we use like 5 gallons per every sack for mixed water to get a 15.8 ppg of slurry, of cement slurry. This year, they are, how would I put it now? They varies depending on the well that you are designing your cement slurry for. There are some wells that are more pressured, higher temperature and all of that. But this is just like a template through which you can design your cement slurry from. So I want you guys to put this in mind for your class G cement. You have a range of, let's say, 4.6 to like say 5.1 mixed waters for gallon per sack for your mixed water. So that's what you have for like your class G cement. To just keep this at the back of our mind. So moving on, still on the mixed water. Say the amount of mixed water that is used to make up the cement slurry is carefully controlled. Yeah, like I said earlier, you want a cement slurry, you want to design a cement slurry that you can easily pump and that won't add in while you are pumping. So here it says that if the water, the mixed water is too much, your cement will not set very strong. Like for those of us that have experience with or that have seen people molding blocks, if there's too much water in your cement mixture with your sand and all of that, you will not have a very solid block. And if your water is not for the cement slurry, if you do not put enough water you see the cement density will be high. It's more like you are mixing, if you don't have enough water to your block molding, what do you get? The thickness will be very, very, because density is more like the thickness now. Your thickness will be very, very high. And for if your density is so high, this you cannot pump it. So you have to be very, very, very careful when mixing your cement slurry with your mixed water. All right, a minute. I want to bring in a fluid engineer that works in a lab that understands the properties of cement, what they measure in the lab. I want to bring her to just talk about the properties of cement for a while, then I will continue after she's done. Please, Golaga Fejiro, if you're on the call, please, you can just go ahead, just give a breakdown of how cement comes into your lab, the kind of tests you guys run, just for the student to understand the properties we look for in a cement slurry.
Okay, good evening, everyone. Please confirm you can hear me.
Yes, ma'am, we can hear you. Please go ahead.
Okay, thank you very much. So I'll be proceeding with how cement, more like the cement reception and how we perform testing. So I'm not speaking on behalf of a company, I'm speaking based on exposure and also experience. So for the cementing, just like your instructor has said, there are a lot of activities that are carried out in the field that the lab is more like the heartbeat of the field, because once you have a proper fluid to be pumped downhole, it becomes a challenge for both the client and also the servicing company. That is very important that we look at several characteristics like the viscosity, we look at the yield points, we also talk about the gel strength. All these fluid loss is also part of it. All these are critical evaluation that the slurry must go through before we can pass a slurry for pumping or before we can optimize the slurry for another design. So like as a fluid engineer, my role involves designing cement slurries for different clients, and then also understanding the behavioral properties of each of the slurry, because we have different kinds of slurry in terms of density and also in terms of temperature, in terms of pressure, in terms of the well, let's just say general wellbore conditions. So well A might not have the same properties as well B. So you have to understand the well environment before you pump a particular kind of cement job. Some cement jobs are designed for gas related fields. Some cement jobs are designed for a field region that may be radioactive in nature, or using a radioactive additive to counter any form of radioactivity that may affect the cementing operations. So how do we receive and what do we do whenever we receive a sample? So sampling is very critical in cementing. I think is one of the priority in most cementing companies, because you don't want to use a sample that will not be used to perform a test and you send to a client, and the client is using another sample. It does not give the representation of the whole volume of what is needed to be used. So for example, an engineer sending a sample like a cement, because we have class G cement, and class G is the major API, although all other cement like the class H, class J, class K, they're also API, but one of the most recommended class of cement that we use generally and globally is the class G cement. So you don't want to send a class G cement that is not from a particular silo or from a particular batch, let's just say from a particular container to the lab, and you are using another cement from a tunnel or from another drum to pump your job. It won't give you the representation of what you want to do. So anything that is being sent to the lab should be to be used in the lab, in the field. If you are sending drill water from the rig to the lab, it should be the same drill water you'll be using in the field. So we have an homogeneous, we have a repeatable results and also a reliable data. So once a client make request for cement fluid design or cement fluid to be pumped, the first thing is to go through the design, ask relevant questions like, why are you using these additives? What is your well condition? Is it an offshore well? Is it a surface, like more like land? Is it a surface job, a surface casing job? Is it an intermediate? Is it a remedial job? So the primary cementing is basically anything that is new, from the primary to the from the surface, intermediate, production, all those ones, conductor, all those ones are just like the primary cementing job. Then we now talk about the remedial cementing job that basically talk about maybe there was an issue in the previous cement job that was done, and you are required to pump in a small portion of cement fluid in a section of the well. So that defines remedial. So we want to know all those information. Okay, by the time we get those information, we are like, okay, we recommend you use so additive because the well is at so temperature. We recommend you don't use this additive because this additive is not compatible with a particular additive on the field. Then the other thing is you want to do, like I mentioned, sampling well data, like real-time well data. Then the other thing is the design of the job. If the client wants a fluid loss additive because they want to prevent kind of losses in the well, you design it to meet the amount of fluid loss that the client wants as minimum or as maximum. Then after the design, we do what we call the measurement. Measurement is getting the appropriate proportion of what is needed. Just like a nurse, when you go for a medical treatment, the nurse knows the dosage that is supposed to give to you. If he's giving you a paracetamol injection, he knows that you cannot take above 50 ml. For example, he knows we can't go above 50 ml. So for the design tells us, okay, this is the maximum concentration of a particular additive to be used per time. Then this is the maximum number of additive not to be used. It also talks about the ability to, okay, sorry. Okay, yeah, so it talks the maximum concentration of the additive to be used. It also tells you that if you are measuring, because most of our measurements are at a degree of accuracy of 0.01 plus minus 0.01 when you're measuring. So whenever you're measuring a particular additive, you use your accuracy factor to avoid overfeeding and reduction. After the measurement, you proceed to the mixing. The mixing, just let me just break it down a little. Cement slurry is made up of your base fluid, additive, and cement. Those are the three, should I say, combination that makes up a slurry. So the base fluid could be your seawater, your drill water, or fresh water. It could also be any of the base fluid you want to use. Then the additives could be solid additives or liquid additives. Then the cement is class G. Sometimes it depends on the well. If the well needs a very high density slurry, you may want to blend it with silica blend in terms of the temperature and also the depth. So the cement slurry can be in form of just class G, and it can also be in form of a blended kind of cement stuff. So after measuring, you do the mixing. You mix the base fluid with your additives. So you mix based on densities. Some Additives are higher in terms of densities, while some are lower in terms of density. So after mixing, you take the rheology. Rheology is very important because if you don't know the properties of your fluid in terms of its plastic viscosity, in terms of yield point, how long this cement can withhold, because one of the properties, I'm trying to merge drilling fluid. One of the property of drilling fluid, which is the mud, is to bring cuttings to the surface and also to hold cuttings in terms of let's say a changeover in the rig. So it's the same thing the slurry is doing. So the slurry should be good, like good in terms of rheological properties, in terms of gel strength, because once you're pumping and at a point you need to stop, will the cement be able to bounce back by the time you resume pumping? Like by the time you put on your pump, will the cement still be able to pump? So after mixing, you take the rheology. After the rheology, if you notice that the density of the slurry or the slurry is too viscous to flow, you redesign again to make sure that the slurry is pumpable. We don't want to pump slurry that the pump will be cavitating or the pump will be going through a lot of stress to pump a job. Then the process, just like I'm doing just like a flow chart. If the rheology is not good, they redesign again to have a proper rheology. So once you're done with the rheology, you go over to the thickening time. The thickening time is one of the most paramount tests we run in cement job because we want to know how much time will it take for the cement to set. We don't want to be pumping a job and all of a sudden they call you notice that the pressure is building up and you observe that the cement has set in your casing. Cement slurry is supposed not to set in your casing. It's supposed to set in the annulus between the casing and the wellbore. So any cement job where the cement sets in the cement casing, like the inner diameter of the casing, it means you must have gotten a clip, CLIP, which is cement left in pipe. And that will lead to a lot of issues. You may want to look for how to, yeah, I should round up, I'm coming. So you may want to look for how to break that cement before you continue your job, or you now have to do a remedial job by plugging that well. Then finally, the thickening time, like I said, is to know when it will stop pumping. And we measure that in bedding units of consistency, known as the BC. So for a tail slurry is higher in density with a lot of cement quantity. So for a tail slurry, usually 70 BC and above, while a lead slurry, lighter in density and also in terms of cement concentration, it's about the POD when there's a point of departure. After the thickening time, you may want to do compressive strength, and the compressive strength tells you how much that cement can withhold stress. So it's usually 50 to 500 psi and also above 500 psi. So a good cement slurry should give you a reasonable compressive strength within 24 hours. And finally, you share your results with your client. And if the client is okay with it gives you feedback. There are some other tests, but I will not go into details. So if the client is okay with it gives you feedback. If it's not okay, you redesign and you start the process all over again. At this point, thank you very much.
All right. Thank you very much, Bulaga Fijiro. So, guys, please confirm you guys can hear me.
We can hear you. We can hear you.
All right. So Bulaga just did justice to what happens in the lab. After all these designs are done, your additives, these are some of your additives. For knowledge sake, you have your accelerator, your retarder, extender, densifier. I'm just trying to rush this presentation. So for your accelerator, just know your accelerators, they reduce the setting time. For your retarders, they extend the setting time. So most time for the accelerators on the field, you add accelerators to your cement slurry for your conductor casing, for your surface casing, because these casings, this whole section, they are not They are not deep, they are shallow hole. So temperature is not usually very high there. So, but for deeper wells with higher temperature, you want to add additives such as retarders and all of that. So extenders is just for you to reduce your density of your slurry. You can use your slurry. For this, most of the time you use a barite. You use barite. So you have your dispersant and other additives such as the deformants to remove foams and gas bubbles, LTM for low circulation and all of that. So basically this is cement slurry. This is what your cement slurry will look like. Your cement slurry is your cement plus your mixed water plus your additives. So after, like what Gulaga Fejiro said, after they are done with the lab, they send this cement to us as a blend in the well site, and this is where we actually come in. So this is how, so these are going to be our cementing equipment. So this is how, if you can see my console, these are silos. This is how the cement comes to the field. The cement comes to the field like this in a powder form, in a blend. You can mix it with the additives when they come and all of that. So these are cementing truck. Here we mix and pump to the wellbore. These are cementing equipment. This we also call this most of the time. This is part of most of the time. We also call this as a part of a casing equipment. So we have the guide shoe and the float shoe. The guide shoe and the float shoe, they are the same thing practically. The only difference is that the float shoe has a float. The float valve is just a non-return valve. You don't want a U-tubing when you are pumping into your wellbore. As you are pumping in your cement, you don't want your cement to come back into your casing. So that's why they have a float here. And usually it's not really as a punter, it's just like a secondary, a secondary barrier, I say, because you also have a float collar in your casing. So for your float shoe is usually made up to the first, or should I call it the last joint of your casing. So other equipment includes your float shoe. So this is your float collar, joint or two joints away from the float shoe. So the float shoe guide the casing into the wellbore, while the float collar is usually two joints above the shoe. A joint of a casing is like that's 30 feet. So two joint, that's 60 feet. So the float collar is usually like 60 feet away from the float shoe. We also have, okay, if you can see this diagram here, this is a representation of what it looks, or what it looks like in the wellbore when your casing and your cementing accessories are already in the wellbore. So this first one here, if you can see my console, this is the guide shoe, which is this, or the float shoe. Most of the times in my own experience, we have always been using the float shoe. So this part here, the difference, or should I say the distance between this float shoe and the float collar, now I'm trying to be fundamental as much as possible, is what we call the shoe joint. So you should know your casing, your slurry that your cementing that you are designing in the wellbore, in the lab that you are taking to the rig site, is going to fill your, here's my console, it's going to fill your annulus and your shoe track. So you should know that your cement is going to be first in your annulus, and then a part of it will also be in your shoe track. So this is the float collar here. These are bottom plug, our top plug. This you are seeing here is a centralizer. I think I have a photo of the centralizer. So these are our plug, top and bottom plug. So our top plug is a solid core. It's solid from the top to the bottom. It's just a solid. It's solid. While for the bottom plug, it has an hole. It has a hole, or should I call it an hole, and then a disc. This disc can be ruptured with pressure. When you apply pressure, that disc can break. And I will explain the sequence later in this presentation. So these are the centralizers. Centralizers basically, like the name implies, is to centralize the casing. You don't want a situation whereby your casing will be tending to one part and then the cement will not be able to cover the annulus very well. You'll be taking some part of the annulus and not some other part of the casing. Another part of the annulus will not be having cement. You don't want that. So you want a good standoff. By standoff, you want a good cement that covers the casing all round. So that's why we use a centralizer. And centralizers are mostly more used in a deviated well, because in deviated wells you'll be having dog legs and all of that, key sitting. So you need a centralizer to actually be able to sending your cement, placing your cement around the casing. So that's just the basic function of the centralizer. So this is the cementing head. Okay, this is a field photo of the cementing head. The cementing head actually is what connects the cementing unit, which is this. I'm sorry, I'm a little bit fast. I'm just trying to try as much as possible to round up. So this is the cementing unit. These are connected with pipes, line, which we call lines. So we connect lines through this cementing truck, which is cementing unit. So to the cementing head. And also our plug, our top and bottom plug are usually secured in the cementing head. I will explain the sequence later. So like I said earlier, cement slurry, this is how you design your cement slurry. The main English that we'll be speaking is just cement, water, additives, you mix them together and then you get your cement slurry. And we should understand in operations, there are two types of cement slurry in operations. We have the tail slurry and the lead slurry. Tail slurry usually has higher density and is much more stronger than the lead slurry. So you can call the tail slurry the strong cement, while the lead slurry, you can call it the weak cement. Please, if you are still following, let me know. If you are still following, please just drop a chat or an emoji. All right, okay, thank you very much. So we should, okay, I've seen that. All right, guys, so basically this is the primary cementing sequence in the well site. After all these slurries have been mixed and all of that, this is what we just do in the well site. It's quite simple, very explanatory. Like I said earlier, we already know this is our cementing head. This is the connections, the manifold connection to the cementing unit. If you can see my console, just follow up my console. This is our bottom plug. The one that has hole inside, the hollow ones, is our bottom plug with a ruptured disc around here. Then we have a solid membrane as our top plug. This here, this looks like a circle, is our centralizer, casing accessories, centralizer. This is our float collar. From this float collar to our float shoe is what we call our, what do you call it again? Can someone help me on the chat box? What do we call this between the float collar and the float shoe? Just to see that we are following. I'm still waiting on you guys. What do we call this? The length between the float collar and the float shoe. All right, okay, thank you very much, Daniel. Yeah, okay, Time B is, if I'm not pronouncing the name very well, sorry about Otabo, he's saying joint. It's not actually just joint because there are a lot of joints of casing. Daniel is actually correct. He said the shoe joint. So these are our shoe joints. You just know that if you are not getting anything from this whole presentation, at least you know there's a thing called shoe joint. So first off, we've made up all of these things. We've lined up all our lineups and all of that. And before we commence the cementing sequence, before we commence cementing, first off, we need to make sure on the website, you need to condition your mud. Usually you can do 1 bottoms up, 2 bottoms up. By 1 bottoms up or 2 bottoms up, I mean you just flow your mud, just circulate your mud from bottoms up 1 or twice. If you do it twice, that's 2 bottoms up. So you condition your mud to be clean, you make sure your hole is clean and all of that. You don't want any contamination to your cement. So those are very important, because if you have contaminated cement, you have a poor cement job. If you have a poor cement job, there's high risk of channeling. High risk of channeling can lead to a blowout, etc. So next up, on these schematics here, if you guys look at these schematics here, what they did first was they dropped the bottom plug. This is just like I think this was the best schematics I could get for this presentation. They dropped the bottom plugs first, but in my own rig, the way we work, we usually pump. So this is not, I'm not saying this is wrong, and there are a lot of different ways people do cementing operation, but for us, we pump in our spacer first. Yes, this is our spacer fluid. You can call it spacer fluid, or you can call it pre-flush. That is, you are saying you want to flush the casing first to remove every form of mud. You don't want your cement to be mixed with your mud. So that's why we pump our spacer first. I'm using my experience of cementing to actually do this lecture. I'm not following the way it is here. So we'll pump our spacer first. After our spacer, there's a valve here, or I call it a plunger, that you release. Once you release the plunger around, here's my console, around here, your bottom plug drops. So what your bottom plug actually does is to clean the ID of the casing from any form of mud that the spacer probably didn't take along with it. So after dropping your bottom plug, you start pumping in your cement. So like I said earlier, there are 2 types of cement we usually use in the industry, which is the tail and the lead slurry. So before I continue, I want someone to just, you can be a guesswork or whatnot. Which do you think they pump first, this tail slurry or the lead slurry? Like I said earlier, the lead slurry is the weak cement, while the tail slurry is the stronger cement. It has higher density. So in your own opinion, which do you think you pump first? Okay, I can see lead. Okay, say lead slurry is pumped first. Daniel. All right, thank you very much, guys. So these guys, they are actually correct. You pump your lead first. Miss Juliana, your hand is raised. Please, you want to say something?
Yes, please. Please, for the sake of time, you have like 5 minutes more. Thank you very much.
All right, okay, thank you very much. So you see, I need to be quite fast. So you pump in your lead slurry. After pumping your lead slurry, you go with your tail slurry. So everything here, you assume this is your lead plus your tail slurry. So when you're done with that, you drop your top plug. Once you drop your top plug, you pump in your displacement fluid. Your displacement fluid, most of the time on the rig, we use a normal drilling mud. So what does it do? The displacement fluid, like the name implies, it's very, very simple. It displaces the cement from the casing into the shoe joint down inside the annulus down inside the annulus. So that's just it. So we just keep displacing until the top plug meets with the bottom plug. I think I missed something around here when I was saying about the ruptured discs for the bottom plug. As you are pumping in as you are displacing and pushing down your top plug, the pressure will break, or should I say, will rupture this bottom plug rupture disc, so that your cement can go through, and all of that. So for your top plug, you just displace with your top plug. When your top plug meets your bottom plug. That's what we call bumping in cementing operations, that, oh, we've bumped our plug, meaning our cement, if we have a successful cement job, meaning our cement is now in our shoe track and in the annulus. So that's just basically everything we do on cementing operation. So when we are done with this, we wait on cement. While we are waiting on cement, we do some wellhead operations and all of that. So I'm trying to be very fast. After that, after wait on cement, you can pressure test your casing, etc. Then how we evaluate our cement, we do a cement bond log. If you watch the Deepwater Horizon movie, you hear them talking about cement bond log. It's just to actually evaluate the bonding of the cement, to know the integrity of the cement job that you just did. So cement bond log, or you do the cement bond log, the CVL and the VDL logs are run together on the field. So since I have 5 minutes more, I wanted us to do a little calculation. So I don't know. That might not be possible, but then again, we should just know when we are designing our cement, we want to know, we don't just go to the field and then just start pumping cement. We need to know, oh, the volumes of cement that we're going to pump, the amount of sack of cement that we're going to use, the mixed water that we're going to mix those sacks of cement, the additives that we're going to add, and all of that. Even for displacement, when we're going to displace, we need to know the volume of mud that we're going to use to displace our cement into the shoe track, down into the annulus, down up the annulus. So all of these are calculations you do prior to even going to the field. So I'll just show you guys, or you guys probably be familiar with the formulas. Say for the cement slurry, we need to place for cement slurry requirement, we need to calculate for the cement in the shoe track. We want our cement to be placed on the shoe track and then inside the annulus. I will talk about this rat hole. I will show you guys the rat hole with a schematics. Okay, so if you can see the schematics here, we already know what a shoe track is. So the space between the float shoe or the guide shoe and the depth of the wellbore, you need to give a little space so that your cement can be pumped through that little space into your annulus. That is what we call our rat hole. So we should know this is a rat hole in cementing operations. So again, we need to know the numbers of cement, the cement sack that we're going to use. So this is a formula for calculating it. The total volume of cement divided by the yield of the cement. That's the total volume of cement you've calculated to pump for that cement job divided by the yield. That's the yield is just basically the amount of cement you can get from each sack of a cement. So that's just it. The mixed water requirement. There's API mixed water requirement. So mixed water, this is the volume. This is a formula to calculate for volume of mixed water. Mixed water per sack times the numbers of sacks. So we need to know for our additives. This is also the formula for our additives. We should know, as a rule of thumb, a sack of cement weighs 94 pounds. So just know that as a rule of thumb. Most of all of these calculations, there's a red book. This is a Aliburton cementing book. There's a blue book, SLB book, and a green book that you can get all of these from basically without much calculations. So this is how to calculate for our displacement volume. If you want to know, the volumes of mud that you are going to pump to displace the cement, this is the formula to calculate it. You calculate the capacity and then you multiply it by the depth, the length. So this was an example I wanted us to do. Ms. Juliana, can I still get another, say, 5 minutes to run this calculation, or I can probably share it with the student, they can do it. The solution is also there. I don't know which will be more fixable.
All right, you can go ahead. 5 minutes. Thank you, sir.
Okay. All right, no problem. Okay, yeah, I can even see someone saying, can I go can you enlighten us a little on the cementing calculation? All right, guys. So I'm still going to rush this. If you don't understand it, you can reach out to me on my personal DM. You can reach out to Juliana. She'll give you my contact, and then probably I'll just explain this little calculation. It's a very simple calculation. So let's say 958 casing, which is a production casing. We're going to cement a production casing. So this is the depth of the casing shoe. This is the O depth. It's a 12¼ O section. So our casing is going to be a 958 casing. From this now, if you are following up my explanation, you know you have a 10-feet rat O. So you have a 10-feet rat O. Their previous casing, hold on, the previous casing was set at 6,200 feet. For this calculation, they are telling us that for this design, let me not use the word calculation, for this design, they're telling us our top of cement should be, for this 958 casing, the top of cement should be 3,000 feet above the shoe joint. So if our top of cement is 3,000 feet above shoe joint, where is our cement going to be? What will be the depth of our cement? Please, I need someone to just quickly do that math. It's a very simple math, and just drop it on the chat box. They are telling us this design is our top of cement is going to be 3,000 feet above the shoe joints. Let me see. Okay, 10,800. Anthony got it. So I think people are following up. So we're going to use a 0.2% D13 arrow retarder. Like I said earlier, if you people understand, I said for a retarder, additives like retarder are mostly used for deep wells, because deeper wells have higher temperature. And as you are pumping in, you don't want as you are pumping and then your cement is setting inside your casing. You don't want that. So you want as much as possible to prolong your thickening time. So that's why the retarder is added. And then again, for this top of cement, I know there might not be enough time to ask questions. The major reason why they are saying, oh, our top of cement is going to be 3,000 feet above 958, and it's not going to come up to the surface of is because you should know this, as it's more like a rule of thumb, I would say, for surface casing, mostly you fill up the annulus to the surface with cement. But for production casing and intermediate casing, most of the time you don't fill them up to the top of to the surface. You don't fill the annulus to the surface, because it's going to cost you and all of that. And basically, major reason why for surface casing they fill up the annulus to the surface is because of the weight that the surface casing is carrying, the weight from the BOP and the wellhead. You don't want your casing to be buckled from all this weight, the axial load that is resting on the casing. So that's why you just fill it up, and that's it. I just hope you guys got that. I'm just trying to be very, very fast. So these are schematics of the example that was just given. Already told us, like someone said, Anthony said our top of cement is going to be 10,800 feet. From the example, our 13-3/8 casing shoe, which is the previous casing, was set at 6,200 feet. Our float collar, I want to see if, okay, it's not here. If someone tell me why our float collar is 13,740 feet? I think this will be the last question I'll ask you, then I'll just be rushing the rest. You know, remember I said our float, the distance between the float collar and the float shoe is usually our shoe joint, and most of the time it's two joints, and a joint of a casing is 30 feet, so it's more like 60 feet. So our shoe joint here is 60 feet. So 60 feet minus the 958 shoe will give you our float collar depth. So that's how they just got the depth. Let me just rush. So the first calculation we're going to be making is we want to calculate the volume the hole is going to take, the hole / the casing is going to take. So first off, we want to calculate the volume of this annulus of the open hole here. If you can see my console, and the casing, the outer diameter of the casing and the inner diameter of the open hole. So we want to calculate the volume of cement that it can take. So like I said earlier, first off, you want to calculate the, I know a lot of us might not really catch up easily. If you can't catch up easily, just reach out to me. I will do the little explanation I can over DM. So first off, you want to know the capacity of the open hole between the casing and the open hole. You want to know the capacity. And what's the formula for the capacity? If you have a pen there, you can just write it down. If you have a pen, I'm just giving you guys like 30 seconds to get a pen if you don't have a pen, or if you have something on your phone, you can write it. The formula for calculating capacity is OD square minus ID square over 10 to 9.46. Let me repeat myself. OD square minus ID square over 10 to 9.46. So we already know our OD, which is the inner diameter of the hole, is 12.25, which is 12.25 square, minus the outer diameter of the casing, which is 958. 958 is 9.625, if I'm not mistaken. Square it, divided by 10 to 9.46. We are going to get this. If you can see my console, you are going to get 0.0558 barrels per foot. So you multiply it by the volume. They already told you in our design that we want our cement, our top of cement, to be 3,000 feet above the shoe joint. So you multiply, that's the length already. So you multiply it. So you multiply, this is what you're going to get. So 167.4 barrels of cement slurry will be what we feel the annulus between the casing and the hole. So from our design, we want to add an SS. We don't know, probably there might be lost circulation, we might lose some cement and all of that. So we want to add an SS maybe for contingency plans. So 20% of this, of 167.4, is going to give us this. So if you add the 20% to it, you should have the 201 barrels of cement slurry for our open hole between the casing and the hole. So next off, we want to calculate for the shoe joints. You know, I said earlier, Miss Juliana is already raising her hand. Miss Juliana is already raising her hand. Okay, Miss Juliana, just give me a minute. Let me just rush through this. So like I said earlier, we want to have our cement in our shoe joint and in our annulus. So for our shoe joint, this is what we calculate for the capacity of the ID of the casing. And if you calculate, this is a theoretical ID. If you look at your red book and your blue book, you are going to see it there. So basically, this is what you are going to get for your, this is slurry, the barrels of slurry you are going to get for your shoe joint. And then you want to calculate for your rat hole. If you calculate for your rat hole, the same formulas, also your 2 barrels, then you add everything together. This will be your total slurry of cement that you are going to pump. So you already know the total volume of your cement that you are going to use for the operations you've designed it. Now you don't need to know the amount. Okay, this is mixed water. You need to know, okay, the amount of sacks of cement you are going to use. So this is a formula for a class G cement with the density of 15.8. We are going to get, like, from all the calculations, you are supposed to get like 1,021 sacks of cement for the operation. For, like I said earlier, there's a standard for mixed water. We're going to use 5 barrels per every sack. So we're going to get something like this 5,105 gallons of mixed water. Then we convert it to barrels, gallon to barrels. This is the conversion factors. 42 barrels make 42 gallons make 1 barrel. So we need to see, that's how we calculate for our amount of additives. And then for our displacement volume for the mole, still calculate. If you don't understand this, I can probably just reach out to me on DM. So thank you very much for listening. I know there was not enough time to explain things in details. Thank you very much. If you have any question, you can ask. Ms. Juliana, over to you. Ms. Juliana.
Right. All right. Thank you very much, Mr. Amos. Thank you so much. We've learned a lot. Just because of the sake of time, I know that if we had given you more time, you would load us with so much knowledge, but I'm very, very sure that
Oh,
we've gained so much. Goodness, if you're on the call, please go ahead. Goodness, can you hear me?
okay. Hello?
I don't know. All right, for the sake of time, please, I would love you all would like to take the photography section. Mr. Amos, please, can you stop sharing your screen? Thank you very much. Okay. Please hold on. We'd like to take the photography session. All right. To help us with the photography session, please just turn on your camera. Would love to see your beautiful faces, your handsome faces. We've had such a great time, right? So we just wanted to take a quick snapshot.
The winners for announcement. I need to say taking the announcement for.
Okay. All right. Please turn on your cameras. I would love to see your beautiful faces, your handsome faces. Yes, there will be a section for question and answer. But for the sake of time, we might not be able to take that. So please just drop, or if you know you have any question now, please just drop it on the chat box. Now will be a very great time to drop it on the chat box, all right? And very soon we will take it. All right. All right. SPE, let me turn on my video as well. Okay. All right. SPE, Solution People Energy. SPE. Miss Abby, please, have you taken a snapshot? SPE, Solution People Energies. SPE, Solution People Energy. I can see your beautiful and handsome faces. Thank you so much for joining us today. All right, before we go on, I would love to recognize the presence of our ALP, the YP co-lead, the person of Engineer Nelson is with us here on the call. Thank you very much, sir, for joining us. All right, Goodness, Kede Goodness, if you're on the call, please go ahead. Okay. Goodness, are you on the call? Can I be heard?
Yeah, we can hear you.
Okay, all right. Okay. I would just want to share my screen. Give me a minute while I do that. So we'll move on to the next agenda for today.
Okay.
Can anyone see my screen? All right, please
Yeah,
confirm
we
you
can
can
see your
hear me.
screen.
All right, sure. All right, on behalf of SPA Worry Session, please, I would like to call on our YP co-chair to help us present the certificate of appreciation to Ambassador Lecturer of today. Engineer Nelson, sir, please, if you're on the call, please, would love you to do the honor to present the certificate to him. Thank you very much.
All right, good evening, everyone. Please confirm you
Evening.
can hear me.
Yes, sir, we can hear you, sir.
All right. A wonderful lecture we've had this evening, and I believe that we have a lot to ask, because I think we've also learned a lot, and I'm also using this opportunity to personally appreciate the speaker for today for taking his time and his efforts to deliver this wonderful lecture, making it as simple as it should be, and also for the benefit of those who don't have the technical experience to grasp what the topic is about, talking about cementing. Yeah, so on behalf of the SP Worry section, the YP, the Young Professionals Committee, would like to say a big appreciation, a big thank you to you for delivering this wonderful ambassador lecture program on fundamentals of cementing from theory to field application. Yeah, and this is just a symbol. It's not enough to say thank you, but it's just a symbol to say thank you for the time, for the efforts, and for everything that you've put into this. We appreciate you so much, and we hope that we'll have you next time when we call upon you. Thank you so much for doing this with us. I appreciate you.
All right. Thank you very much, sir. Thank you. The voice you just heard is the voice of our YP co-chair, Engineer Nelson. And thank you to our speaker for teaching us. All right. Moving on. Kede Goodness, our moderator, please, are you on the call? Can you hear me?
Good evening. I'm on the call. Can you hear me?
I can hear you, but your network is kind of glitching. But please go ahead. Carry on, please. Goodness, if you're speaking, I can't hear you.
Okay.
All right. I think the network thing is.
No, please just go on.
All
Just
right,
go on.
I think the
Having
network
issues.
issues.
Sorry
Just go
for
because of the sake of
that.
time.
I'm
All right,
having some
thank you.
network issues. Okay, thank you
All
so
right.
much, Mr. Amos, once again for that. That was a very long. Oh,
Kede Goodness. All right, thank you very much. I think the network is really something today. All right, to move on with the question and answer session, I would love to call on Confidence. She's the Assistant General Secretary of SPPTI. Confidence, please take one or two questions from the chat box for the sake of time, right? But if you have any other questions for our ambassador lecturer, please connect with him on LinkedIn. We'll also share his contact. But just for the sake of time, because we have Slido quiz, other activities are coming up in this program, amazing prizes to be won. For the sake of time, please take one question. All right, Confidence, please come up. If you can hear me, are you on the call?
Yeah, I'm on the call. Good evening,
All right.
everyone. I would like to say a really big thank you to Mr. Amos for that wonderful and impactful session. We truly appreciate the valuable insights and knowledge you shared, Mr. Amos. And now, at this point, we move into the question and answer session, where we are to ask questions, seek clarifications, and engage further in today's discussion. Now, if you have questions, do well to raise your virtual hand up. If you don't know how to navigate, you just see the three dots on the right bottom, click it, and then you see the raise hand feature. And do well to make sure your questions rather are brief due to time constraints. So I'll be heading over to the chat box. I have the first question from Felix Otiaru. I'm sorry for the wrong pronunciation. It says, how do we determine the density of the cement, or is it fixed? Mr. Amos, if you can hear me, Felix Otiaru asked a question.
Yeah, I can hear you. Confirm you can hear me, please.
Yeah, we can hear you, Mr. Amos.
All right. Okay. To answer that question, let me just quickly just share something. Please, Juliana or AB, can you just share me, make me a co-host? I just want to show him a table to answer that question, please.
Maybe please make it a co-host. Thank you.
All right. Confirm you can see my screen right now. Please confirm you can see my screen.
You can see your screen, sir.
Okay, so for the person that asked the question, there's a standard for every slurry. Usually our slurry is usually of higher density than our mud. So this is like a template, an API template, or should I use an API standard. It varies depending on the well, but usually it doesn't fall far from these values, from this weight here. It doesn't fall far from it. So for a class G, you might actually see a density of class G 15.9, 15.8, or a little less and all of that, but it falls within this range. And how do you measure it? You use your mud balance, pressurized mud balance, and all of that. That's how you measure it. And for your second question, you're asking, let me check the question again. So I will just answer it once and for all. You're asking, so what are the observable consequences of bad cementing in operations? Okay, let me show you the consequences of bad cementing in operation. All right, give me a minute. Okay, you see this image right here? This is the consequences of bad cementing operation. Like this is the peak of it all, which is a blowout. You might have issues like channeling. Once there is channeling, and probably, okay, gas is now going through through those porous medium in the cement. Probably once it comes to the surface, it's already a blowout. It's already a blowout once it comes to the surface. So you don't want a poor cement job. There are some poor cement job that you can, there are remedies for it easily, but basically this is just the peak of it all for a poor cement job. Deepwater Horizon went down because of a poor cement job. I think that should answer your question.
Thank you so much, Mr. Amos. Felix, hope that answers your question. So the second question in the chat box is also from Felix, which says, what are the observable consequences of bad cementing in operations? I'm sure he must have answered your question in the first question, right, Mr. Amos? His answer is in the
I've answered that.
Okay, thank you so much, Mr. Amos. Due to time constraints, I think this will come to the end of the question and answer session. Like our moderator said, if you have more questions for Mr. Amos, do well to link up with him on LinkedIn and ask your questions. Thank you so much once again. Over to you, the moderator.
Thank you very much. Thank you very much. Thank you very much, Amos. I can see that we all have lots of questions, and I apologize because we'll not be able to take more questions. Thank you for sharing your insights. But moving on, we'll be going straight to the Slido quiz. Please don't go. We have amazing prizes for the first, second, and third position. To help us with this is my colleague, the person of Miss Abby Bobomi. She's the ALP co-lead. Miss Abby, if you're on the call, please go ahead. Thank you.
All right, good evening, everybody.
Please confirm, can you hear me?
Yes, we can hear you.
Right, so I'm going to share my screen now, and I'm just going to walk you guys through how. Okay, let me share the link on the chat box so that everyone can join in. Okay, please give me a minute, few seconds right after.
All right, while she's coming up, please, I would like to implore on our ambassador lecturer, Mr. Amos, please share your LinkedIn profile for us on the chat box, right? So that each and every one of us can connect with you, you know, ask our questions for more insights and everything that we want to know. Thank you very much. And thank you to everybody that's been on the call up to this moment. Please don't go. Call your friends to come back. We have amazing prizes for you. Okay?
Okay, so I'm trying to share the Slido code, but it's not coming up. I'm trying to do that, but I just shared the link. I don't know if this is going to work. To share my screen now. So.
Okay. So please start joining in. Start joining in. Send to your friends. We have good prizes, amazing prizes to be won. Thank you very much. Thank you to our distinguished students, our participants for staying up till this time on this call. Thank you very much. Okay.
All right. So okay, so I'll need you guys to go to slido.com. I'm sorry if there's any background noise. I'm currently in transit, so go to slido.com. I'm supposed to share my screen, but I don't know how to do this. Let me try. Okay. This is going to show the questions. Right. Please, I want to get responses if you've joined in or if you are, so that I can start it from my end. I'm having trouble sharing it here. This is the code 4504815. 4504815. I'll take it again. 4504815. That's the code. You just need to put it there on the field and click on join. If you've joined in, I'll see it here. Oh my gosh. All right, so I have your daddy here. I don't know why you chose that name, but your daddy, Daniel just joined in, Felix just joined in, Benjamin, and I have Confidence. I think Confidence is the only female here. So are we ready? Because it's time 10 seconds, and within 10 seconds, you have to give the response. I'm still trying to share. I don't know if I can't let me try and share this. I don't know if this is going to work.
Don't worry, you can go ahead. Just
All
try,
right.
but if you can't, just go ahead.
All right, so we have about four persons in already. So I'm just going to start. I don't know. I would like people to join in with your real names so that I can locate you guys at the end of the quiz. But so persons are joining with okay, that's fine. So we'll go with the first question. The first question, it says, what is the common name for the first stage of cement poured pump ahead of the main slurry? Is it spacer? Is it lead slurry? Is it tail slurry? Okay, so we have more people buzzing in for lead slurry. So let's see. Baby hands are okay. So yes, the leaderboard has it. We have Felix topping the leaderboard. And the answer to that question is A, which is the spacer. So move to the next question. All right. What tool is run on a wire line to evaluate cement bond quality? Caliper log, CBL or ultrasonic log, gamma ray log. Okay, we have a lot of persons buzzing in for ultrasonic log. So let's see. All right, ultrasonic log is correct. What's the leaderboard like? We still have Felix topping every other person's here. I was expecting your daddy to be topping, but your daddy is at the last. So let's see. Next question. Free water in cement slurry test indicates what? Good compressive strength, water separating from slurry, fast setting time, or low density. What's the answer? Okay, free water or free water. Somebody's saying good compressive strength. So let's see. All right, so the correct answer is water separating from slurry. And the leaderboard, we now have Felix being displaced by Olurodere. I don't know if I pronounced that correctly. So let's move to the next question. What is channeling in cementing? I think our speaker spoke about this. Yeah. Is it bypassing the mud, leaving voids or unseat sections, or creating channels for better production? So let's see what the leaderboard's like. All right. So we have Olorundere still topping. So let's see the next question. What is the primary purpose of primary cementing? 1, to cool the debris bits, to provide zonal isolation between formations, or to increase draining speed. Okay. Let's see what the leaderboard is like. So we have Olorode still topping, followed by me and Timile. Let's move on to the next question. Okay, what is the cement slurry property that measures thickness and resistance to flow, density or compressive strength, or viscosity or heat strength? What's the leaderboard like? So we have viscosity as the correct answer. So let's see the leaderboard. We still have Olorundere still. I'll just call him Dare still topping. Right. The next question. Which additive is used to slow down cement thickening time? Accelerator like or retarder like dispersant or antifoam? Let's read the answer. Okay, so we have option B as the correct answer. Okay, let's see the leaderboard. So we still have Dairy topping. Next question. What is the common name for the first stage of cement pumped ahead of the main slurry, spacer or lead? Sorry. All right, so we have spacer as the answer. I think this is all of it. All right, I think we still have like 2 questions to go. Please confirm you can hear me, please.
Yes, we can hear you. Go ahead, please.
All right. So I'm going to the next question. The next question says, API Class G cement is most similar to which construction cement? Is it type 1 Portland, type 3 ILE, or type 5 sulfate resistant? What's the answer? Okay. So we have type 1 Portland as the correct answer. And what's the leaderboard like? We have me topping the shots, and we have confidence coming second. That's nice. So let's move on to the next question. How many days did the speaker said he spent on a cementing operation? If you're listening very well, I think you get this. 6 to 10 hours, 2 days, 1 week, or 4 days. So let's see. 6 to 10 hours is correct. And what's the leaderboard like? This is the final one. And we have me topping the charts, following to, I said chat, topping the poll. And we have Dere coming as second and Confidence coming as third. Congratulations to the winners. Thank you very much. Over to you, moderator.
All right. Congratulations to the winners. Thank you, my colleague, for anchoring this session. This one like you're a winner, right? All right. So please, for all the winners, please reach out to the ALP colleague, the person of Miss Abby Bobomi. She would share more details in the chat box. All right. For the sake of time, we'll just be moving on to the next agenda, and that is the membership drive. All right. The membership drive is just simple. Just in case you're joining us here for the first time, a friend invited you. This is SP section 104 Worry. And what we do at SPE, this is a place where you get first-hand career information. You get access to webinars like this, useful webinars like this, access to mentorship from seasoned professionals, scholarship, access to our vast network of library and knowledge base. You get to network with people and lots more. So if you're a student and you joined in today, please reach out to your chapter president. And if you're a YP, you could reach out to me, you could reach out to my colleague, and we'll put it through. We also have our YP chair on the call. You could also reach out to him, Engineer Nelson, and we'll be very happy to put it on. I'm sure you've been wondering, who has been talking since? I'm just acting instead of the moderator. My name is Juliana Oche, and I am the ALP lead for SPE Worry section. It has been my distinct honor to start this program. I would also like to thank you all, my distinguished participants, the two schools we collaborated with, University of Calabar and PTI, for your strong dedication, even up till this moment. Normally would not be here by this time, but you all still speed. Thank you very much. We don't take that for granted. On behalf of SP Section 104 Worry, we are truly grateful and we are happy that you joined us for this Ambassador Lecture Program. All right, to wrap it up, I would love to call on Ugumadu Benjamin. He's a marine engineer at Tanager Offshore. Ugumadu Ben, if you're on the call, please kindly unmute and help us with the closing remarks. Benjamin, please, if you can hear me, you are muted. Please kindly unmute and help us with the closing remark. Can anyone hear me?
I can hear you loud and clear.
All right. Ben is on the call. Benjamin, I can see him on the call, but I don't know if it's speaking.
Can you hear me?
Okay, I think we can hear you now.
Oh, wait, pardon, please. My network is out. Once again, good evening, everyone. I'm Ugumadu Benjamin. I'll be taking the closing remark for this awesome section. Notwithstanding, once again, I welcome each and every one of you to Society of Petroleum Engineer, Section 104, Worry section. The speaker, Mr. Amos, have done justice towards the foundation, or should I say what the fundamentals of cementing. Most of us thought that cementing is all about mixing sand and then just pour it. But now we have a better understanding that it's about pressure, placement, zone isolation, low density, a lot more. Okay, so this section was quite insightful. It was knowledge-driven, and most importantly, it was interactive. So a huge thank you to our speaker, Mr. Amos, for breaking down this technical section in a way that connects theory with practical section. And also, a huge thank you to each and every one of us who joined in this section. Just like what Ms. Ogene Fejiro said during the opening remark, that we should share our knowledge, we should not be stingy with the knowledge. So I'm encouraging each and every one of us to go on LinkedIn, post about what you learned today. Yeah, I'm quite excited. So post about what you learned today and tag SPE YP section 104 Worry section. Stay curious, stay driven, and keep pushing towards excellence. Have a great night for each and every one of you. Thank you.
Thank you very much. Thank you. Thank you very much, Benjamin. Thank you, Mr. Amos. Thank you, everyone. You all are the MVP. We'll call it a good night today.
Yeah, good night, everyone.
Good night.
All right, good night, everyone. Thank you, Miss Juliana. Thank you very much. Thank you, Bethel. All right.
Thank you. Bye, everyone.
Bye.
And happy Workers' Day in advance. Make sure that your holiday well. Bye.
All right.